Thank you everyone for coming on a Friday morning. This is the first lecture we had together, so see Fridays a little more casual. You can interrupt me even more. I figured I'll give you a little bit more of an outline of what I'm hoping to do with you guys this semester. Of course, it's the engineering school of MIT, so we'll talk about engineering. The specific purpose of my 12-hour module is give you a good sense on materials processing. And I think I started at a relatively basic level, saying, you know, you have these wrought products, you have these castings. I mentioned extrusion. I didn't want to get too much into it. And then I started walking in. You know, last time you guys saw the press for doing a die casting, and you know, we started getting really into some of the details. I showed you those dendrites and all sorts of things. So what I was hoping to do just before we get too far here is I want you guys to really understand how we make parts and why we do it this way. And I will finish up today essentially on castings, and that's going to include plastics. So I got some relatively complex plastic part that we're going to go over. And some of it, again, is going to relate a little bit more to engineering than real, you know, polymer engineering or polymer processing. But I think that's my understanding over time is that's the right level for this class. I do warn you that the upcoming 3 lectures, you guys are going to have to go through. For me, it was 2 years of undergrads, but I will not make it any more terrible than what I did with making parts. So what we're going to do is we will talk about grains. That was something that came out. I had a big meeting yesterday in Tulsa with a lot of people, and there was this engineer, significantly older than me, you know, another expert on metallurgy, and whenever somebody would ask him a question, they'll throw the word molecule, okay? And there is just no need for it because, of course, it blows everybody's mind off. Because if you look at business people, they heard of the word molecule, but they really don't want to know anything about it. If you say grains, a lot of times they don't mind. You know, if you've got a sand pile, it's got grains of sand. It makes sense, you know? So I'm going to try to go through that process with you in terms of metallurgy. And when you feel like, oh, this is a little too much, just tell me, ask questions. You know, that's the way that we've been working already. So I'm very confident that both you and I are going to go through this successfully. And then we'll talk more about other things. Like there was a word last class about, oh, can we make parts out of the powder? You know, these laser sintering and stuff like that. Well, my personal point of view is I'd like you guys to be able to walk, just like my twins, before you start running and talking about really, really like technological development. So that's a little bit my approach. I guess it's how I do things. So we'll talk more about, you can make a surface treatment, you can add a coating for corrosion protection. There's so many things you can do as part of processing. So you start with something that's just steel, and then it becomes something else. Joining, I mentioned it on the first class, is something very, very important. And I have just a very first good case study on that, 2 case studies on that today that I want to introduce. So the reason I'm bringing it down, and I'm going to keep that in my mind, and I'm going to keep you in your mind as well, is when you start putting together your notes, you can decide to follow this outline. You know, you don't have to keep it all, you know, just as a flow, because there are topics, is what I'm saying. Now, there is one thing I want to say is I made reference to Professor Eager's module, but I did not realize how much he's changing you for you guys. So when I said, as you heard from Professor Eager, we use a lot of steel as opposed to concrete and all that, well, he's going to get to it later with you guys this semester. So he just changed a little bit his module. The first 3 or 4 hours are really, really nice overviews. But I don't know how far you guys are going to be able to get in the 12 hours in the details of material selection, because what used to be the first 4 hours now, as I understand it, is going to be lecture 5 to 7 or 8, maybe up to 12, because he has tremendous experience and he's an engineer, scientist, professor, everything. So you guys are lucky. I want to take his class one more time, but I can't do it this semester. So you guys can tell me a little bit about it, maybe in your questions. Okay, so having said all that, yeah, let's get started. Last time, talked about steel being really, really hot, coming from the melt, making these big broom or billets. These are billets. It's what you need to do. You're refining the chemistry of the alloy. You adjust all these alloying elements to have the best phase diagram you want, then you cast the damn thing, and you get these very complex structure. So we talked a little bit about the nucleation of these grains when you solidify that you can make single crystals, but it's a lot harder than just having polycrystals. And then we talked about segregation, chemical segregation. That is the pushing of the alloying element towards the center of the billet when you make it. I talked about sand casting, die casting. I gave you guys the example of making jewelry out of platinum. So we're going to finish up a little bit some of those examples today, and go a little bit deeper on the casting fundamentals. So it's a graduate school class, right? So we will go a little bit more into the chemistry and physics. The material deformation is actually going to be next time. So I changed the slides, but this outline here, we're not going to get to the third bullet, although we will talk about plastic. I got some very specific example. This one is probably not going to run easily, so let's see. I think it's very useful, and I'll relate to why we're doing this. By the way, the lecture notes up, including today, are on the Stellar site. And also for Monday, it's going to be Professor Eager. So we are moving the schedule around a little bit. It's just based on some changes and other commitments. So if we go to the schedule and the class home, right now, for next week, Professor Eager is going to do Monday, Tuesday. Brian is going to do Wednesday. And I will be back for Thursday. I wish I could talk. I like Friday lectures, but it's a holiday next week, so we're not going to have a lecture. Although we'll try to make Thursday lecture. It'll be Friday. And then the following week, I'm traveling, but essentially, it's going to be a lot of Professor Eager the last week of September, and then the first week of October, I just block myself, so I turn down commitment to go places so I can be with you guys and we can finish this up. Okay, so I wanted to show the video for one specific reason. And we talked about this melt of metal being really hot. I mean, even boiling water is kind of hot, right? So it's 100 degrees. So if you think about aluminum, 600 degrees, yeah, you don't want to put your hand into it, and you can probably agree with me. So it's a different process. They always clean those molds when they're going to do a die casting. And it's the oxidation. There's always a layer of oxidation from the molten metal. And I know there was this very specific question you guys had about why don't we do it on vacuum? Well, I think we can all agree that this equipment, if it has to operate under a controlled atmosphere of vacuum, it's going to be a lot more expensive. So we'll make, electron microscope. Yeah, so it's hot. So when it's pouring, you don't want to be there. I've been there. I've seen some stuff blow, and we'll go over that. It just burns through stuff, at that kind of temperature, especially for steel. You can see these are making, there was a piston coming out to make the inside of this. So it casts and then it's pulling out. And that's how you make a lot of car components in large volume. Die castings are very typical for the housing of a pump and things like that. So here comes your aluminum, just the way it is. You didn't think it was this way, right? Yeah, I knew it. That may be all the excitement there is here, but there's a reaction going on. We know that aluminum is has a very strong tendency to oxidize. So when you pick it up there, it makes this little layer of oxide on the top of the pool, but then when you pour it, you expose new material, and that's how you get the flame. All right, so enough entertainment. I think that's the only video I have for you guys today. I'm gonna have to move a little more. Okay. One day I'll learn how to make these run for my presentation, so I don't have to do all this. So I did mention that, but I didn't show it last time as far as making wheels out of this. Excellent. All done at once. And it can be good looking too. You have to go to a very special polishing process if it's made out of aluminum and you want to have it look like a lot of those do these days. So in this specific case, the liquid aluminum alloy comes from the underside and feels all around at the same time. And there's a lot of different parts to that mold. So we have the underside, we have a side here, and then we have a top. It's actually not that bad. But all the engineering associated with cooling to make this is so important, because you want to be sure that you always fill your mold all the way to the end, and whenever the last metal solidifies is where you're going to have porosity. So you don't want that to be an area of high stress. So some of the geometry here is not just for the look, but also for the processing. If you're going to make a component like this, there are shapes you just can't do. So it becomes a part of your overall design as a mechanical engineer to talk to the shop as to what they can and cannot do. That may be a good place for me to go back here before we go into this. Yes. Okay. So again, we're wrapping up here. This is our last lecture about casting. The first class, I talked about when we make something, let's say it's a natural gas plumbing system. It goes into your home and it feeds all the appliances. The last thing you want is a complete pullout of a joint, because that means a big stream of natural gas all of a sudden filling up the house. That's not acceptable. So what you need, if you're not going to have somebody doing, say, the welding, somebody coming up for the inspection of that welding and then using all very, very sophisticated industrial processes, then you ask for fittings that are threaded, like this one. And if you take the material of the casting and you make it a malleable, we haven't talked about this too much, but you make it malleable or ductile iron, it means that it will deform before it breaks. And you do the same with these threads, then what's going to happen is, if your connection was not put on correctly, or something happened, there was some settlement, some forces from the outside, the freezing cycle, you get a small leak. And we have detectors, we smell it, and we know that there's something going on. But the last thing you want is this thing to have a brittle failure. So it just comes into experience and understanding the consequences of a failure on deciding if this is the way to go or not. Is it the easiest way? No. This is terrible to do for a plumber, because all these threads, when you come and have one pipe and you try to put the fitting, you have to get it at the right location, and then you have the other one that you threaded in. When it's done, you can't take it off. So you have to build your plumbing system from one side to the other. They would just rather come with some torches and do some other things, but it's not as safe. So this is, the building code. Another example that relates to how we select things. No, we're going to do this one later. All right. Casting processes. Last time there was a very good question in the class about, okay, what's the size of these things, that the broom or the billet? I said it depends. That's kind of a lawyer's answer, but the truth is it will be a function of what you're trying to do. I gave the example, if you're trying to make aluminum foil or a very thin plate of steel for a car body, you would rather not start with something this big. It's just going to be a lot of work to thin it down all the way to a millimeter thickness. So I talked about this strip caster where you feed 2 rolls here, and you have this little pool of liquid that's solidified. It's a very, very effective process for making parts quickly, but it's subject to a lot of variation. You can probably see here what happens is these rolls have to be fairly cold, so you completely solidify the shell when it's coming out of here. That means that when it's touching the metal, it's cooling the metal quickly. and that means you need to keep feeding that little pool and go at a certain feed rate that's pretty high. So it will come out of here maybe a foot or 2 foot a second. So what does that mean is the filling of that pool with the metal, the liquid metal, has to be so steady and so controlled as well, so you don't have variation in that pool sitting there. So I guess all I'm saying is a lot of process optimization to make those things work, and they're easier with certain things than others. So for aluminum, this process is easy because of the cooler temperature. I did some research back 12 years ago on using it for copper, and copper is around 1200 degrees centigrade, so it was a lot harder. And then getting this to work with steel is higher temperature, so it's even more work. So it's just the way it is. The same with die casting. I gave you guys plenty of example now of aluminum. Well, it's not done with steel. Is it going to be done one day? Probably, but at this point, if you can't make it out of an aluminum alloy, well, you'd like to get it out of plastic, and that's what we're going to finish the class with today, because it's very, very effective. With aluminum, sometimes you have distortion, and I mentioned this, but I'm going to throw it as an image. If your feedstock for the die casting of aluminum contains some solids to begin with, you're going to have a more homogeneous microstructure through the thickness, and it's a process that's a lot easier to control. The other case, the traditional way, is you get this is a cross-section of those dendrites that we looked at together. Okay, so going a little bit more into what happens during solidification. This is a simple textbook. The first one, Porter E. Sterling. There is a more sophisticated version for the course 3 people. It's one of the first year class, Kinetics of Material. Has a lot more, random walk theory and things that are useful, but it's at the same time takes more time to get the concepts right. So concepts. You have a liquid and you want to go through a phase transformation. That sounds really nice, but what it means is all of a sudden you're going to create interface. So if you think about your energy, you have 2 aspects to this. You really have the volume energy, and then you have a surface energy. And by the way, some other may think of this more complex than this, but that's all I can think of. So The liquid would like to become a solid. Let's say it's a dendrite of aluminum. But in going through that process, so in lowering, you want to lower your volume energy, but your surface energy is going up because now you have an interface between a solid and a liquid. So what happens really for a lot of phase transformations is there is a critical size where this does balance out. And I'm showing it graphically here. So delta G is the entire energy. So it's a combination of, if you were to transform, to make a sphere, so as a function of sphere diameter, of course you are reducing your volume energy. So I think we can all understand that because the phase diagram tells us I'm going to transform. Now, what happens is I'm also creating that interface between the liquid and the solid. So when you add it up is where you see that your total free energy is going up until a certain point, and after that, it's going back down. So all transformations are this way. So when we're going to talk about aging of aluminum, it's the same thing. You got to be in a condition where by random walk vibration, you can get over that hump. What's other way to make sure you get over that hump? So there's the best one is to wait. You know, things just bounce back and forth. If you're playing anything with balls, and you know, eventually it's going to fall to the ground. It's just a question of time. If it's ping pong or anything like that, you know, eventually it will follow gravity. Not right away, but it's the same here. So let's say I want to make an aluminum casting that has a very, very fine microstructure. What I'm trying to do is I could do two things. Is I could keep the temperature just below the fusion point, and then what happens there is it's going to take a while before something starts to form, and then that thing that forms is going to grow very, very quickly. That's very typical. If I lower the temperature, what happens is I get these little nuclei that are going to form very quickly, but then they take more time to grow, and that gives me a better microstructure. So it's one basic reason why we would like to cool things relatively quickly, to form more grains, essentially, and have a more homogeneous microstructure. And part of that is this kinetic. Now, one thing that, this is really, really a theory to some extent, especially for metals, because metals, if you don't have a little bit of an interface to begin with, so if you try to get a little solid of silver into a huge vat of silver, this table tells you here you're going to be 200 degrees below the melting point of silver before you start having a solid. And at that point, you know, it's not hot enough. It may not even happen. So we call that the supercooling, and it's I guess it's to emphasize how significant the surface energy is. So what happens? For metal, it starts from the mold. And the reason for that is when you have your pool of liquid metal, there is always an interface already between the liquid and the mold. That's high energy to begin with. So what you do is when you start to nucleate there, is you're replacing essentially a liquid to solid interface with a solid to solid interface. That's great. So it's the only reason, the same way that you get you know, a snow ice formation on the window as opposed to cubes of ice out of the air, is there's a site for nucleation on the mold. It's extremely important for metals, not so much for plastics. And And I decided to go on and talk a little bit about this. And when I do that, you guys can ask any question because I know about it a lot. If you're not interested, that's fine. But somebody asked me, what the hell is this last time? So it is an experiment that didn't work the way it was supposed to. So it's a leftover of this system here where you have a block with an inlet and an outlet tube to do an experiment where, how are we going to do this here? Okay. Yeah, this is all closed. There's more complexity here than you probably want to see. But the basic idea is to study solidification and the effect of the mold characteristics. I had to build this fixture where essentially you expose the surface of the metal with the mold. So the mold just looked like this on one side with protection on the edges. And that was just a big box. And behind of it, you have these spots where you keep track of temperature. So you get the temperature over time to know what happens. So let's say you get that box. So it's all insulated all around. It's got a cooling system to it. Then it has a surface. You lower it into the melt. And it's very close to that strip caster that we talked about with the two wheels coming down. So the purpose of the experiment was specifically to look at what happens with different condition of the roll surface into this nucleation process. All right, I think that's better than this is most horrible, just like molecules. So we're looking here at the piece, the strip of copper, and I'm sorry I couldn't keep any of them. The piece of copper that built over this substrate or mold surface or roller surface, for the analogy to the strip caster. And you can probably see these little deposits or castings have a different surface morphology. So we're looking at about 2-3 inches in size. So this one here has maybe like 5 bumps. Here you're looking at 25 bumps, 10 bumps, there 10. Oh, this is really, really bad. Got this big one bump there. So what happened? So these numbers here is the level of refinement of the sandpaper used to prepare the surface. When it's a very high number, it's a high number of particle per square inch. So that means it's very, very fine polish. So with a very, very fine polish, it was hard to have nucleation sites. So this one spot that I didn't do perfectly, or the one, it was perfect, but it was still the only place that the first nuclei could start from, led to these 2 big bumps on the surface. So the significance of this research, it was actually significant. By the way, it wasn't all my ideas back then. I was, the doer. Just to be clear, just like you guys sometimes. So you have these 2 strips that are forming on each side of the strip caster where they meet. If it's a big bump against a big bump and all that, it's not going to work. It's going to give you a terrible product. So what you have to do is use a very coarse grid of sandpaper to prepare the surface so you get plenty of nucleation site. And you strip, yeah, it had a bunch of bumps, but they're all about the same and they're not that thick. So it's almost homogeneous. And yeah, that's the story. Yes?
So every single one of them are polished?
They're prepared so you have a controlled condition, yes. I can't even remember the one. I don't know why polished ended up on this side, to tell you the truth. Apparently, maybe that's something they did after I finished my internship. They got somebody else that was a better polisher, and he was able not to get any bump on it. But it's not realistic, right? If you get this industrial equipment, You can't say I'm going to suspension polish it so it looks just like a mirror all the time. So the best you can do is say it's going to be a fine finish. So yeah, so this one should be going all the way up here in terms of the evolution. But it's against, you can't do that. Yes?
So what happened to the...
Oh, it wasn't me. But to speak, very good question. To speak about safety, the guy that was the system control for lowering this thing into the melt and picking it up at a certain rate, certain time, and all that, he did an upgrade to the software. And we were really in the middle. No, we were in the middle of testing. Like we would test almost every morning at that point. You want to do it in the morning. It's physically intense to have all that gear on. You don't want to do that in the afternoon. It's just not safe. So first thing in the morning, we'll show up there, get everything ready, and then he only told me after the test that he had done an upgrade to the software. Not that at that age, I will say just run it, but it just went down an extra inch or so, and that's what happened. And then I was down for 2 weeks trying to remake the entire assembly. But we got it done. So maybe the last thing associated with this discretion is safety is very important, and anything you do, you never know what's going to happen, especially in R&D, because we were very, very close to the end of the program, and now this happens, and then you got to start all over again. So it's not as when you're doing these things at high temperature with a lot of variable, like how much stuff you put into the oven to melt it, and which alloy you use, and what's available, and is it really too moist today, because you can't have any moisture from the AC system going into that. A lot of considerations, and then so you're able to run, but you never know which day you're going to have to shut down for a couple of weeks. That's what I call R&D. You don't know. You hope you can continue generating good results. So some of the other results, I've talked about the thermocouple here. So keeping track of the temperature evolution was giving us our heat transfer coefficient. Maybe the only thing I'll say there, because we talk about casting that is relevant, is when you look on a plot here, let's say that's the thickness direction for the deposit. And so TH, not confuse it with time. What happens is you're going to have a temperature of your mold. In our case, that's the copper here. That's fairly low. Not that I would touch it, but it doesn't melt, right? We're looking at maybe a couple hundred degrees is all it does to this side, where because of the cooling system, mainly, and also when you solidify, you create an interface. That's the reason for this slide. I want you guys to understand that you have the liquid metal on the other side, that's 1200, and you have that big gap here, delta T, and then if you combine that with a certain constant, that's your heat transfer coefficient, it gives you the energy transfer across the mold interface. So the significance of this parameter for processing is money. If I can transfer the heat more quickly and safely and with a good quality product, I want to do that. I don't, because even our die casting that I've showed you, you see it's closing. It takes a couple minutes. It's not like a press that goes and make little knots and bolts very, very quickly. So the two things that we've talked about so far for casting is nucleation. And then here, this is a second concept, is you have to transfer the heat. When you start to solidify, you have to transfer the heat. And if you have these big bumps like this, I use the argument that I didn't want a bump to come against the other bump, but that's not the only reason why I don't want big bumps. If I have these big bumps, all of a sudden the shell that I'm creating is deforming physically. So you'll have a contact here where you started, and all the surrounding area is going to bow and not touch. And it reduces my heat transfer coefficient on the interface. So there's so many reasons why you really want to try to get a good contact between your metal and the mold and keep it regular. So in the case of die casting, the fact that you apply a pressure, just that itself helps you keep that contact constant. So if this sheet is trying to rip off, there's a fluid pressure behind it that forces it to touch. It's one reason why a pressure casting is a better process than just gravity casting. All right. So we want to avoid those, and we talked about the fact that we want alloys because it's a lower melting point here than it is to have the pure alloy. I've also mentioned that it allows you to get very intricate into the microstructure. What I realized is this: if you were paying attention last time, you probably got it, how we make a phase diagram. If not, you can either go back or you can ask me about it, because I love phase diagram. Thermodynamic was one of the things I was good at. I couldn't do it the way I used to, though, because I'm not using it as much. So thermodynamic in terms of metallurgy, for processing, we use it for heat treatment. So we're going to go to that later. And we use it tremendously to control the quality of the steel that we use for casting. So what happens is, if you have a steel that has a lot of contamination in it, you in this process prior to casting, you have a slag on top of that casting, of that melt, and by the high temperature, the high energy, you can have a chemistry of that slag that it's going to be like a sponge, and it's going to pick up those impurities you don't want and move them to that phase, and then you can toss it off after that. So there's just a lot of thermodynamic used in metallurgy, but the basic concept is this free energy and trying to minimize it. And what we've talked about last time is, if I have a certain energy for a certain phase, another phase, this without the interface. So this analysis here has no consideration about our surface energy. This is just for the volume. It's how we determine this one. It tells me, well, I would rather have a certain fraction of this phase and a certain fraction of this phase, as opposed to having just one phase that has a higher average energy here for each of the two phases. That's how you minimize your volume total free energy. A lot of phase diagrams end up looking like this, where the first thing to solidify, and that's, I didn't bring any cursors. I'll just draw it. So the first thing to solidify is going to be more rich on, say, iron here. If we say that's going to carbon. So what happens is, I have this pure iron that's going to solidify. The diagram's a little more complex, and this is my concentration. I got these two lines because this is the stability. So let's say up to this point, and I got to stop it because this is very high temperature. It's not the equilibrium phase we have at ambient temperature. So this is a phase here. It only has one concentration, and this is the liquid. So just the same way we were discussing it with the free energy, when I come to this point here and I want to make the alpha phase, then this alpha phase is going to have this concentration, so it's moving backward. And that's the reason why it's going to be pushing all the alloying element into the melt. Yes?
Do you have like a way to visualize different phases?
Which phase?
Like just different phases. Like is it like arrangement of atoms? Is that like what you mean?
Yeah, and I'll bring that. So essentially here it's completely random. It's amorphous or a glass geometry, and here it really is a crystal phase. And so to get that organization, it's why a lot of, let's say you have manganese in there and you have carbon, they don't really want to be in this crystal structure. They get pushed into the melt. It's a very good question.
So when you have that like alpha phase,
Yes.
you want to have here, and you have the other phase that you want to have below. What does that look like? Is it like there's a huge part that's alpha and a huge part that's the other, or is it like all mixed together?
Very good question. So the question is, what happens when you try to do this? It will be in two different ways. So the first way, if this is our situation where it stays as a liquid and the other one is an alpha phase, what happens here is it will typically have these protrusion forming to push away the alloying elements, and you form these dendrites. So it's one grain into a liquid is what happens then. And just like we discussed, you want to try to have as many of these as possible around your mold so it stays regular. If it is going to transform into two solids, then that's where you get more of your lamellar structure, where you have your alpha and say your beta, because then they just, up here, they just do an exchange of what each other doesn't like, and they grow simultaneously together. And we see that a lot. That's our perlite that we're going to go through. So that's a little bit what this explains here. Graphically, maybe a little better, where your first solid is going to have less alloying element and it's going into a liquid. So when you make your part, when you're done, what happens is the surface is going to be more pure than the very center. And one implication of that is how you're going to need to be at high temperature and do all this hot rolling so you can get this gradient back to homogeneous if it's required for the application. This is a little bit more complex here, but it's how you would calculate to know if you're going to be forming big dendrites or not. So there's a critical rate at which it will happen or not, and I can't go to that. I'm going to get trapped in for 10 minutes or 20 minutes. Yes?
If you like made a video of this happening and then you wanted to do the exact reverse thing by adding temperature,
Yeah.
would it like look exactly like you playing the video backwards? Like does it happen the same way if you just reverse?
A very good question. So when you melt, we don't study that as much. I almost had to think about it. Well, the first thing that's going to happen when you heat it up, it does sort of mix in by diffusion a little bit. So everything at higher temperature, we're going to go through that. You get grain growth, you get certain boundaries to disappear, you get your chemical gradient to disappear, because now you have those two phases, and it's not the equilibrium. It's just the way you did because you did it quickly. Let's put it this way. If you did quickly enough, I think it would be the reverse, but we don't do that very often, and we never really go through the process. If you do it slowly, you will probably end up closer to equilibrium before you melt. It's a very good question. It's a little tough one. All right, plastic. So I'm showing you these little pellets here. So a lot of times, if you're making parts like this, you'll start with a feedstock that looks like cat food or something. And what you do is you do have to heat it up. So what I'm showing here is a typical system for injection molding. They don't call it die casting, but it's a similar process where you heat up your plastic, you put it into this drive system. It is a screw, so it's heated by, and it's blended by shear deformation. This screw, just like a food processor, if you've ever ground beef here, that's what happens. Eventually it gets into your mold. The best beauty of this, it's so low temperature. It's so easy to do, so everything happens very quickly. You can make more quickly. Your mold material is less expensive. It doesn't wear as much. So we'd love to make everything out of plastic if we could. Now, this is probably where I'm trying to make sure I get you guys to see a little bit both sides. What still happens here, I'm showing the flow into the mold, is we talked about these, well, we got to use molecules. Are you guys okay with that for here? Yeah, good. You're engineers, so. So the big, long chains of molecules, they get oriented here towards the mold, close to the mold. It's not exactly like forming grains of crystals. You can probably think of this because everything is just so long that you cannot organize a macromolecule spaghetti into something that's very, very organized. It's just not going to happen. But what does happen is when you push it, you shear it, and you deform it, you form that skin. So it turns out, if anything you want to bring home for your permanent knowledge base is, if I go and start grinding the surface and trying to make it polish, it's not going to be as resistant to creep and fatigue and cracking than just the original material. Most of the time, the as molded geometry is more resistance because you form that skin. Now, what happens more towards the center is this slide that I skipped. So you form crystallites and spherulites. Did I have the word written down here? No, I can write that one down because it's so important. I mean, when you think of polyethylene, polypropylene, nylon, they all have this structure internally, so they are semi-crystalline polymers. So let's see here. Spherulite. These are about the same size, so it's micrometers in size, and as opposed to the metals, you have a lot more of these nuclei forming in the center of the part at the mid-wall. What happens, so you start from the very center, you start forming an arrangement, so you fold that molecule into a crystal shape, and then it grows from there, and eventually it merges with the next one. So it's just little assemblies, because it's not crystals, there's thousands of crystals in each one. And the idea is a little bit like we were talking about here, where there are two things. So you say, I'm going to send you what is disorganized and take what I can organize, and that's how you form those crystallites. They have a lot of implications for the quality of a part. The same way you want to have these fines. I worked on Nano Composites, and what happens there is sometimes if you have your little particle of reinforcement that act as a catalyst for forming these things, then you can control the size of your spherulite that way. So each little particle is going to be a point of initiation. If it's a nano clay material, then it may grow in one direction and form a ladder structure as opposed to forming a sphere. So just so many implications of how things start from the melt to having a solid. So hopefully that completes our first 3 hours. We'll close it, and if people have more questions, because we can't really hear.